Okay, everybody. This is a general overview of some of the things we covered in statistics. I'm going to start off with some general ideas, definitions, concepts that you should know when you walk in to take that final exam. So, Chapter 4, we got the basic definition of probability. You know exactly what the makeup of the population is in terms of actual numbers. Now, this is important. We know the actual numbers that make up the population. You should be able to count your way through the problem, working on or with the basic definition of probability, which is the probability of an event is the number of ways it can occur divided by the number of ways anything can occur. In other words, if you know how many things belong to the population, I have a population of 200 people, 20 drink Coke, 40 drink Pepsi, etc. That sort of setup. Then most likely, if it's a probability question, you should be counting your way through it. Now, with that said, can you identify a few properties of probability? You should pause the video and think about this. So, as we go through this, you should be pausing the video, thinking about the problem, then playing the video to see my response. All right? So, I will take a deep breath to give you that opportunity, unless I forget. So, what are a few properties of probability? One, it's always between 0 and 1. Okay? That's just based upon the definition up here. How can the numerator ever be larger than the denominator? How could the numerator or denominator be negative? When you add up the outcome probabilities, they add up to 1. And then another rule that we like to look at and keep in mind is what I call the complement rule, or opposites. The probability of opposite adds up to 100%. So if 40% of the students are taking math, we know 60% are not taking math because those two things are opposites. Got it? Another concept is the concept of permutations and combinations. These were counting techniques, right? They are both based on counting the number of ways one can select several different objects from the same group of objects. So you are choosing several different items from the same group. Permutation versus combination. Now, a permutation is identified with the word order, meaning when something is selected, it makes a difference. The notation we have here is given by P of n pick or. We're choosing from n objects or different objects, right? And again, you have a button on your calculator. You should have one that calculates that for you. Excuse me. The combination. The combination's associated with no order, meaning you don't know, it doesn't matter when you get selected. You're being selected, and that's all there is to it. Permutation, order. Combination, no order. I need the president. I need a vice president. I need two people. The first one was a permutation. The second was a combination. Notation-wise, C of n pick or. I'm picking from n objects or objects. And again, there's no order. So here are a couple of examples of this. And you try to decide which one they associate with. So again, stop the video. All right, our first one. Select 7 people from a group of 6 men and 8 women. I'm picking 7 people. So I know this is a combination. Because again, if I pick you first, or I'll pick you 5th, you're just a person being selected, right? There's no indication that the order in which I selected you makes a difference. Now, what's the notation? Well, how many am I picking from? I'm picking from 14 people. I'm picking 7. Use your calculator to get the answer. Okay? Again, just keep in mind, I didn't say there had to be so many men or women, so I am just looking at the 14 people in total. The next one, select the president and vice president of the math club. We're going to choose them from 12 students. This is a permutation. Why? Because when you get selected, you are being labeled differently. The first one is the president. The second person selected is the vice president. I'm choosing from 12 people. How many am I choosing? 2. Once again, you have a calculator. Calculate your answer. All right? The next one. Select 3 men and 4 women from a group of 6 men and 8 women. This really consists of 2 combinations, right? I'm going to pick 3 men. Didn't say anything about order. Just pick 3 men. But the 3 men have to be picked from the 6 men. So combination of 6, pick 3. The 4 women are going to be picked from 8 women. 8, pick 4. And we multiply these 2 numbers together. Okay? For us, when we're counting, it will be multiplication. So, there you go. Okay, what can you tell me about the binomial distribution? So pause the video and think about, if I asked you, explain the binomial distribution to me. What do you know about it? What are you going to tell me? I'm going to tell you something there we go. 1, it's an experiment that is being repeated multiple times, that is, n trials. So, I have a box of 100 light bulbs. I'm testing to see if they're good or bad. That is, there are 2 possible outcomes. Good, bad, yes, no, true, false, etc. Now, to me, this is one of the biggest things that helps me identify the problem. You are counting the number of times one of those outcomes occurs. I get 4 bad light bulbs. I get 7 bad light bulbs. 8 of them were correct. 9 were correct. 6 people were drinking Coke, etc. You are saying how many. So if it's a binomial probability problem, it's usually the probability you get 4, the probability you get 7, the probability you get 3. You're counting. The mean is n times p, right? N is the number of trials. P is the probability of what you're counting, success. The standard deviation is sigma, equal to the square root of NPQ. Okay? Now, here are a number of examples to illustrate this. We have a sample of 20 dogs. How many weigh more than 15 pounds? 4, 6, 10, out 20. Out of a group of 20 students, how many are taking math? So again, the probability question would be saying the probability 4 take math, 6 take math. A gardener sows 300 seeds. How many germinate? 3 of them do, 4 of them do. Once again, each one of these can be looked in terms of either one of 2 outcomes. They weigh more or they don't weigh more. They're taking math or they're not taking math. They germinated, they did not germinate. Each of these are counting and would be asking about the probability of that many. As we go through this little workshop here, it will be assumed you know how to work with the standard normal table. I'm really not going to explain that except in this particular slide here. Remember, when you work with the standard normal table, it is telling us the percentage of data that's below a number, the probability of being less than a number, the area below the number, okay? So, you are looking at the normal distribution you have a number Z, and the table is telling you this area here, what's below this number, which is the percent, which is the probability of being below that number. There are essentially three fundamental scenarios. What are they? They are: 1, it's exactly what the table is telling us. That is, we're asking the probability we are below a number. Right here. Exactly what the table is saying. That was scenario 1. Scenario 2, it is opposite of what the table tells us. We are above the number. So it's 1 minus what the table was telling us, right? The opposite, right? In other words, if I look at the little diagram up here, I'll get rid of that, and I will be above the number, right? But again, the table is telling us what's below it. Those are opposites, and so since they're opposites, we're subtracting from 1. Scenario 3. The difference between the two numbers in the table tells us, right? But the difference between the two numbers, the table tells us what? The probability being between the numbers is the difference between the two numbers in the table. I kind of messed that up, but got it? If I'm looking for the probability of being between the two numbers, it's the difference between the two numbers in the table. So I have a Z1, I have a Z2. I want to be between these two numbers. Well, I get this number from the table here. I get this number from the table here, and I take their difference, right? Whatever that number is, whatever that number is. Got it? Again, it's assumed you know how to do this, okay? Because that's fundamental to most of what we do in the second half of the course. Okay, how would you distinguish between using Chevyshev's and the empirical rule? So you should talk to yourself about what you know about Chevyshev's and the empirical rule. All right? Here we go. Chevyshev says nothing about how the data is distributed. The empirical rule problems will say that the data has a bell-shaped distribution. So Chevyshev says nothing. Empirical rule says bell-shaped. Both of them are about approximating, estimating the percent of data in an interval. Approximating percent of data in an interval. Now, again, that's what the question's about. If it says nothing about the data distribution, you'd be working with Chevyshev's. If it said bell-shaped, you'd be using empirical rule. If it had the word normal in it, you'd be using the normal table. We'll see that in the next slide, okay? The mean weight of a cupcake at Cupcake World is 5.5 ounces. It has a standard deviation of 0.25. I want you to estimate the percentage of cupcakes that will weigh between 4.8 and 6.2 ounces. So here's a problem. We're going to just talk about it. I'll probably kind of work it out for you, set it up for you, because we're really just talking theory here. Well, here's a problem. Well, first thing I see is they're asking me to estimate the percentage of cupcakes that's in an interval. Okay? They're in an interval. I see nothing about how the data is distributed. I don't see bell-shaped. I don't see the word normal. This is Chevyshev's. Okay? So, Chevyshev's two formulas. One has to do with the interval. Another has to do with the percent, right? For our interval, we have the mean. We look at the endpoint, 6.2. The distance from here to here is 0.7. So the relationship between that distance and the number of standard deviations, k, is given by d equal to k times sigma. So you substitute in 0.7 here, you substitute in 0.25 here, you can solve for k. Once you have the value of k, the approximate percentage is 1 minus 1 over k squared, right? Enter that into the calculator. So again, working with Chevyshev's empirical rule, you have two formulas. One's the distance related to the standard deviation in terms of k standard deviation units, and the other one is the percentage related to k. All right? All right. Now, there are essentially three types of probability problems for which we use the normal table to determine the answers. And they are a probability problem where we're talking about a normal population, a probability problem where we're talking about the sample mean, a probability problem where we're talking about a proportion of the population. These three types of probability problems lend themselves to working with the normal table. And how do we get to the normal table? We subtract the mean, we divide by the standard deviation of whatever we are talking about. Well, in the previous slide, remember, similar problems, but one problem said nothing about the population's distribution. The second problem said something about it, but they said it was bell-shaped. Both problems were similar to a probability problem, but they really talked in terms of estimating a percentage of the population, right? Never talked about the mean, sample mean, I mean. Never really talking about a proportion. Now, the word proportion can be used in other contexts, okay? Well, this example is the example of the population being normal. You read the problem. I'm going to point out the key words here. Again, you can stop the video. Normally distributed. Probability a member of the population. Okay. I know I'm going to be working to get to the table, working with this right here. Right? Then I'd be using get to the table formula. The second one, read it. Again, you can stop the video. Well, I'm asking about the probability of the sample mean. I'm talking about the sample mean here. I'm talking about the probability of being between 4.8, and that's x bar now, and 6.2. The fact that I'm using x bar, though, you know you're not going to work directly with sigma. You're going to be working with sigma divided by the square root of 30, right? To get to the table. All right. Next one. Excuse me, I got a cold now, so I'm coughing. Anyway, got to get it done, right? Probability problem about a proportion of the population. Okay. Well, the proportion of cupcakes at Cupcake World weighs something. Determine the probability. The sample proportion weighs between 4.8 and 6.2. So, again, we're talking about the proportion of cupcakes that weigh between this is less than 60%. Here's the question here. Remember, you're talking a proportion, so you know you're not working with 4.8, 6.2. That's not a proportion, right? That's proportion in this context would be between 0 and 100%. We want the sample proportion to be less than 0.6. That's what we're looking for. Now, the difference too is, again, you're going to be subtracting the population proportion divided by the sample proportion standard deviation, right? Which is the square root of p times 1 minus p over n, right? I'm not going to write that down. Some of the things you really should know. All right? So, if I'm talking about a proportion, again, you know you're automatically going to the normal table. You'd be working with the population proportion, subtracting that, right? Then you'd be calculating sigma of p hat, right? Square root p times 1 minus p over n. Got it? Okay, let's describe when and how you can use the normal distribution to approximate a binomial distribution. Now, these problems tend to be lengthy and I guess a little bit more difficult in terms of calculations. But anyway, so what do you have to do? Think about it. Here's what I have to say. 1, when the product of n times p is greater than 10 and the product nq is greater than 10, then you can approximate the binomial probability by a normal. Okay? You're going to have to make this half-point adjustment to your numbers. What I'm saying here, if x was binomial and I was looking at the probability that x was less than 5, I would make an adjustment to take in consideration we're going to a continuous distribution. I don't want to include the 5. I'm going in this direction, so I'm going to have to go to 4.5. Okay? Let's do another one. If I had an equal sign here, then again I'd be going in this direction. Here's 5, but this time I want to include the 5. So if I want to include the 5 and I'm going in the left direction, I would have to start at 5.5. One more. Okay? If I was asking probability that x is between, say, 6 and 9, including the 9, not including the 6. So again, x is counting how many, more than 6, but fewer than or equal to 9. Remember, x is binomial. You're counting how many. Well, in this situation, here's 9, here's 6. From the 6, I am going in this direction. Well, I don't want to include the 6, so I'd have to start at 6.5. For the 9, I am moving in this direction because I'm below the 9, but I want to include the 9 here. So if I want to include it, I'm going to have to start above the 9 at 9.5. That is what we mean by the 5-point adjustment. This is the only time going to a normal distribution in order to approximate a binomial distribution. Next, you will get to the table once you make your adjustment. In other words, we'd have the probability of 6.5 less than x less than or equal to 9.5. I would be subtracting the mean and dividing by the standard deviation and then working with the third scenario of the table between two numbers. Now from this point forward, we're going to be working random problems. Just random problems. So who knows what you're going to see on the next screen. But we're going to talk about identification and methodology. Okay? Once again, as we go through these, I hope you are stopping the video and working the problem. All right? Okay, here's our first example here. Now, if you have the printout, remember the example numbers are random. Okay? But it does sort of match, it does match up with what was on the paper, but when I put them in here, they're random. So always make sure you look at what example number you're working with. All right, you read the problem. I'm not going to read it to you. So you should be stopping the video right now. Remember, if I say stop, stop it, read it, and then start playing it. All right. This problem is asking you to approximate the percentage of cupcakes that weigh between 4.8 and 6.2. I'm approximating a percentage of the population, all right, in some interval. Nothing is being said about the distribution. This is Chevyshevs. Okay? Nothing said about the population's distribution. I don't see the word normal. I don't see the word bell shape. So I have my interval 5.5. I need one of my endpoints, which is 6.2. Again, if you look at 4.8, you're going to have the same distance. That distance is 0.7. That distance is 0.7, like a finer looking pen. But anyway, that's the distance. We know the distance is k times sigma. Sigma in the problem is 0.25. You solve for k. And you can show yourself k is equal to 2.8. Okay, so I have the interval. I found the distance to the endpoint. I know that's equal to k times sigma, so sigma from the problem. K then is equal to, by solving for, 2.8. Now, since I'm working with Chevyshevs, the percentage relationship to k is 1 minus 1 over k squared. I substitute in k. You do the math. If you did the math correctly, and I did the math correctly, which I believe I did it twice, I get 0.87. So about 87%, at least really for Chevyshevs, okay? Chevyshevs, it's really at least that. Well, 87%. There you go. Okay, if you do have the handout, I did change these two numbers here. So keep that in mind when I work this problem out. So you should stop the video now and work this problem. Alright, here we go. We're trying to determine the probability associated with the sample mean. The probability associated with the sample mean. We know we need to get to the table. And in order to get to the table, we're going to have to determine the mean and the standard deviation. But here's the question. The probability that X bar is between 5.3 and 5.6. Now, the mean is the population mean, but the standard deviation is for X bar, which is 0.25 divided by the square root of 30. Well, if you do your math, show yourself this is 0.0456. So I am now going to convert this to the z-score. The probability 5.3 minus 5.5 divided by the standard deviation. This is 6. This is now a z-score. Okay. 5.6 minus 5.5 divided by 0.0456. When you do this work, you're going to have the probability between a negative 4.38 and 2.19. Well, your z-scores 0.9854 minus, well, we're really off the table here at the left-hand side, so it's really close to 0. So you might be a little bit different than my number here, but we're going to be close, okay? You should be somewhere near 98.5, something like that, okay? But that's my answer. You should be very close to this number here. Once again, I did change my numbers here. We're talking about the probability of the sample mean. We're going to the normal table. Here's the normal table formula, right? Normal table formula, right? Got the normal table numbers, our z-scores. This is the third scenario. We take the difference between the probabilities. Got it? Okay, consider this next example here. Stop the video. Alright, histograms. You need to identify the histogram based upon the data distribution. Do you suspect the data distribution is right skewed, left skewed, bell shaped, or uniform? Okay, so you decide. Since this distribution, let me change my color here to green, maybe Delgado green. Notice that this distribution has a left tail, right? So we say it is left skewed. Well, this distribution has a right tail, so we say right tail distribution, right? Our next one, this one sort of goes straight across. It might have some waves in it, but it's sort of like a horizontal line. Uniform. And our last one, this one sort of looks like a bell. To me, it looks like a hill. All right, it has two tails, bell shaped. So there you go. Histograms help us identify the data distribution. So, right skewed, left skewed, bell shaped, uniform. All right, stop the video and read this particular example and try to determine how you're going to solve it. And then you might want to stop the video again and then try to solve it. But anyway, here we go. The problem's asking you to estimate the probability a cupcake weighs between 5 and 6 ounces, assuming the cupcake weights have a bell-shaped distribution. So again, we're estimating. Now typically this would say percentage, but it does say probability, and we're estimating, and we have the word bell-shaped. That is suggesting the empirical rule, okay? So this is suggesting the empirical rule. All right, meaning my first step here is going to be coming up with an interval centered at the mean. The end point of the interval is 6, so my distance from here to the end is 0.5. My distance is k times sigma. So 0.5 is k times sigma, which is 0.25 right here. When I solve for k is equal to 2. If you're working with the empirical rule, you know you should be getting either 1, 2, or 3 for your value for k. And if you're 1 standard deviation away, 68%. If you're 2 standard deviations away, 95%. If you're 3 standard deviations away, 99.7%. We are 2 standard deviations away, so approximately 95% of the data is going to be between these two numbers. That is, 95% of the cupcakes are going to weigh around between 5 and 6 ounces. All right, read problem number 6. So stop the video because I'm going to start talking about it. All right, let me fix my pen. For some reason, it keeps All right, here we go. Let's look at the following table, and we're asking you several probability questions. What you should be noting here is a couple of things. You're given the population in terms of how many. I know how many people are in the population. It's this right here. There's 145 people that participated in this survey. All right. I also know how they're classified. How many are classified? 60 like loud music. There are 85 teenagers. There are 60 adults. And here we go. One person selected at random, and we want the probability they are a teenager and they like soft music. So, and means you have to satisfy both. So, if they need to be a teenager and they need to like soft music, that is 30, right? There's my 30. Now, What is the denominator? I didn't tell you anything else in terms of who I picked, meaning I have to assume they're coming from the 45. So there are 30 ways to pick a teenager liking soft music. There are 145 ways of choosing somebody. So 30 over 145, I will let you convert that to a decimal number. Part B, I want the probability they are a teenager. Now here's a very important word here, given they like soft music. I know these people like soft music. The person selected, likes soft music. If I know they like soft music, I know I'm pulling from this particular column here. How many ways can I choose a teenager in this column? 30. How many ways can I choose somebody from this column? 70. So see the difference between and given, right? I didn't say anything about the person selected in A, but I did tell you something that I know that they are. They were picked, they liked soft music. The question is it an adult or a teenager? C, the probability that they're an adult or they like loud music. So this is an or. When you work with an or, let me change my color here. When you work with an or, you don't care which one. So they could be an adult. Well, if they're an adult, I have 60 ways of choosing them. They could be a person that likes loud music. There are 60 ways to pick a loud music person, right? But if you look at the adult row and you look at the loud music row, these 10 people were included in both these numbers, so I have to back them out because I included them twice. So you do your math and you get 110. Question is, what is the denominator? The denominator is 145. Why? I didn't tell you anything about the person selected. I'm asking if they're an adult or they like loud music. All right? So again, can you describe the difference between A and B? So let me clear everything out here. Okay. Well, A, you're saying and. You're not saying anything about exactly who they were when they were selected. Given says you know the person selected did like soft music. So you restricted it to this column here. Okay? Why do you have to be careful working with the word or? Well, if you look back at our problem, maybe I'll kind of get a thicker thing, marker here. Well, that's too thick, huh? But anyway, a little bit thinner, and I'll erase that. Okay, let's erase everything. Why not? Anyway, yeah, squirrel here. Not the weight, man. Okay. Anyway, or. Well, they're an adult, or they like loud music. Those 10 people got counted twice in these two numbers, so we had to back them out. Got it? Moving on. Okay, stop the video and read the problem, and I'm going to get started talking about it. All right. We have a question about the probability that a cupcake weighs between 4.8 and 6.2 ounces. We are assuming the cupcake weights are normally distributed. Very important word there. Normally distributed. So, normally distributed, probability of a member of the population, we need to get to the table. That is the probability that X is between 4.8 and 6.2. You need to get to the table, right? Well, we're talking about a member of the population, so we will be subtracting the mean, right? Which is 5.5, divided by the standard deviation of 0.25. Now we're working with a z-score. Likewise for the 6.2, subtract the mean, divided by the standard deviation. Notice we did not adjust the standard deviation because we're talking about a member of the population. You do your math, and you get negative 2.8 here. You get 2.8 here. Okay, well, that's the third scenario in the table. You look up 2.8. When you look up 2.8, you get 0.9974. When you look up negative 2.8, you get 0.0026. And when you do the math, you get 0.9948 for your answer. So if you got somewhere close to 99%, you're looking good. All right, moving on. Okay, next example. Again, this is example 13. You need to approximate, I'm sorry, you read it. We're going to get started here. Stop the video. Okay, if you look at this particular problem here, they want us to find the probability that 10 take calculus. Well, if I want to know the probability that 10 of the 16 are taking calculus, I must be counting how many. That indicates this is a binomial problem, right? Binomial. Okay? Meaning that we're looking for the probability that x is equal to 10. Well, the formula for a binomial is, first, you need to decide how many ways you can pick 10 of the 16 students. That's C of 16, pick 10. All right? I'll fix that here. You need to figure out the probability of picking 10 that take calculus. Well, for each one, it's a 55% chance. There are 10 of them. Well, if there are 10 that are taking calculus, the other 6 are not taking calculus, and the probability they don't take calculus is 0.45. Doing the math, this is 8,008. This is 0.025. This is 0.0083, which is equal to about 0.66 or 16.6%, 17%, whatever. Next question. How many do you expect to take calculus? Well, this again is binomial. I expect n times p to take calculus. N, 16, p, 55%, right? So 16 times 55% is 8.8. So expect 8.8 people to take calculus of the 16. All right, the next problem. Stop the video, read it, work it out, play the video. All right, this is a probability about the sample proportion. The probability about the sample proportion, we need to get to the table. So the question here is asking, what's the probability the sample proportion is less than 0.65? Well, in order to get to the table, we need the mean, and the mean is the population proportion, which is 0.7. The standard deviation is the square root of p times 1 minus p divided by the sample size, which is 36. When you do your math, this comes out to be 0.0764. So now we have everything we need to get to the table. So this is the probability that z is less than 0.65 minus 0.7 divided by 0.0764. Doing our math, z is less than a negative 0.65. This is exactly what the table tells us. So we look the number up in the table, and we get 2578. So again, Probability about the sample proportion, let's get to the table. Subtract the mean, divide by the standard deviation. And again, for proportion, standard deviation is square root of p times 1 minus p over n. All right, read this example here. Stop the video, and I'm going to work it out for you. Okay. Now, at a recent art show, paintings were placed in one of 5 different categories. 7 were listed as New Wave, 10 were listed as Victorian, 17 as Abstract, 22 as Really Weird. One painting is selected at random, and we want the probability it is a really weird painting. Now, this again is a probability problem where we know exactly how many items are in the population and categories. So we should be able to count our way through this problem. Can you tell me how many ways you can pick a really weird painting? There are 22 of them. Can you tell me how many ways I can pick any painting? Well, 7, 17, 34, 56. There are 56 ways to pick anything. So 22 over 56, and then you would write that in a decimal form, most likely 2 places. All right? So again, probability where we know exactly how many items are in the population and we can count our way through the problem. Okay, ready for the next one? Again, stop the video, give it a try. Is it possible for the following to represent a probability distribution? Well, you have 2 definite things you need to know in terms of probability. Probability has to be between 0 and 1. So if we look at all of the outcomes, each one of the probabilities is between 0 and 1. The second thing we need is the total probability for all outcomes has to add up to 1. So we have, let's erase this, 5, 20, 25, 75, 100%. So the 2 conditions are satisfied. Probabilities between 0 and 1, and they add up to 1. Again, a question like this, we don't care about the outcomes. Outcomes are what they are. Next problem. All right, read it. Stop the video. All right, here I go. We need to determine the probability the committee selected will have 2 teachers and 1 administrator on it. Probability problem where we know what the population is made up of. We should be able to count our way through the problem. So, the general problem is just forming a committee of 3 people. Okay, 3 people to be selected to form a committee. We're looking for a particular makeup of that committee. It needs to have 2 teachers. It needs to have 1 administrator. Well, the probability we choose 2 teachers, 1 administrator is the number of ways we get 2 teachers, 1 administrator. The probability then is, the denominator is the number of ways we just simply pick 3 people, right? Well, if we need 2 teachers, the 2 teachers have to come from the 7 teachers. Doesn't matter what order, you just need them on the committee. If we need 1 administrator, that 1 administrator has to come from the 5 administrators. Again, no order. If you look at the denominator here, Well, we need just 3 people. Those 3 people are being selected from the 12 people in total. Because again, for the denominator, there's no particular makeup that was necessary. Just 3 people. So you do your math. Well, C of, excuse me, C of 7 pick 2 is 21. C of 5 pick 1 is 5. C of 12 pick 3 is 220. That's your button on your calculator, right? So our numerator is 21 times 5. Our denominator is 220. So we have 105 divided by 220. You do the math from this point because again, they typically want a decimal number. So this is a very straightforward problem, honestly. You're looking for the probability of choosing 2 teachers, 1 administrator. You know exactly what the population is composed of. And again, here's the definition of probability here. I have 3 separate calculations, which basically the calculator takes care of. Then you multiply the numerators, and then you divide by the denominator. Okay, here we go with example number 14. Again, I'd suggest pausing the video here. I'm about to work it. Alright, if you look at this particular problem, they want you to find the probability that a randomly selected mortgage payment is more than $1,000. So they're looking at the probability that X is larger than 1,000, right? Now, mortgage payments are approximately normally distributed. So we're going to be getting to the table. Since we are talking about a mortgage payment, a member of the population, we get to the table by subtracting the mean and dividing by the standard deviation. So in other words, this is equal to the probability that Z is greater than 1,000 minus 1,000 minus 982 divided by 180, which is the probability of Z being greater than 0.1. Well, that's opposite of what the table tells us. So when we look up 0.1 in the table and we find 0.5398, if you take the difference between that and 1, you're going to get your answer, which is, let's see if I can do that by no calculator here. Okay, it would be 54, and 54 is 46, so 0.4602. That's what that should be. All right. Between 1,000 and 475. But once again, we're talking something normally distributed, a member of the population. So between 1,000 and 1,475. Once again, you're going to get to the table. Now I'm going to skip this part here, but again, this is what we're doing here. We're subtracting 982, we're dividing by 180. Show yourself that your next step would be 0.1. Closing my parentheses a little bit too early. Z. And for 1475, when you do the math, you're going to get 2.74. You look these two numbers up in the table, and it's going to be 0.9969 minus 0.5398. Doing the math, you get 0.4571. And so there's the probability of being between the two. All right, example 08. Read the problem. Stop the video. I'm about to work it. All right, so we know 45.7% of students at Delgado are taking courses online. We want the probability they do not take any courses online. These two things are opposites. Since they are opposites, our answer is simply the complement property, the opposites property. And so you take 100%, subtract from that the 45.7%, and here's your answer, 54.3%. All right, so that's not bad at all, huh? Example 12. We want to compute the mean for the following probability distribution. So once again, pause the video, work it, and then replay, start the video right back up. So here I go. All right, if we're going to calculate the the mean for a probability distribution, your job is you multiply outcomes to their respective probabilities. That's our first step. Outcomes get multiplied to respective probabilities. We get negative 0.1. And then you're going to be adding these things up. 1.1 times 0.25. When you multiply these two, you get 0.275. 2 times 0.35, 0.7. 0 times anything is 0. And for the last one, you get 0.875. So we're multiplying each outcome to its respective probability. We're adding them up. And when I add them up, I get 1.75. So the mean is 1.75. Problem 15. Again, pause the video, read the problem, then get back with me. All right, for this problem, we are being asked the probability of the sample mean, okay? We took a sample and we're looking for the probability the sample mean will be less than 23.8. That is the probability that X bar is less than 23.8. Since we're working with X bar, we need to get to the table. In order to get to the table, we know we need to subtract the mean. Well, the mean in this problem here for X bar is that of the population, 24.3. We need to figure out the standard deviation of the sample mean, which is whatever the standard deviation is in the problem, divided by the square root of the sample size. When you do the math, sigma is equal to 0.52. Now that we have the mean and the standard deviation, we're ready to get to the table. We subtract the mean. We divide by the standard deviation. We have a calculator that works. And when we calculate that number, 0.96, this is exactly what the table is telling us. So we look up this number in the table and we get 1685. Example number 10. Pause the video, read the problem. Here I go. All right, so we have a game of chance. There are 3 possible outcomes. You can win, you can lose, or you can draw. Is it possible for the probability of winning to be 0.5, losing 0.45, coming to a draw 0.06? Well, we have all possible outcomes. Probabilities have to be between 0 and 1, which they are. but they need to add up to 1. Well, when you add these up, you get 1.01, which is not 1. So the answer to this is no. All right, number 17. We'll just get going here. You can stop the video. Find the z-value in the normal table such that 68.08% of the data lies to the left of z. If you remember, the normal table that we work with basically tells us the probability of being below a particular number, right? So we're told, the table tells us what this number is. Well, we want this number to be 0.6808. In other words, we're working backwards. We're looking at all the probabilities, and we hope we find this number here or the nearest number to it. Well, if you look in your table, you'll find 6808. If you look to the left, you see the tenths position of the z-score. If you look above that, you're going to see the hundredths place for the z-score. So the z-value for which 68.808% of the data lies below that number, 0.47. Now for number 18. Now for this one here, I'm only going to set up the problem for you because there's just too much going on here. So I'm going to set it up, and then you can actually do the math yourself, right? So read the problem. Pause the video. All right. This is a binomial problem because we're looking for the probability that at least take calculus, at least or more than 8 takes calculus, at fewer than 8 takes calculus. Whatever, we're counting how many are taking calculus out of a group of 25. So this is binomial. They want us to use the normal approximation to the binomial. Well, if you're going to use the normal approximation, the first thing you're going to have to do is do the half-point adjustment, right? Well, for the first one, we want to be at least 8. So we're going to be going in this direction, right? Now we want to include the 8, so we want the 8 included, so we're going to have to start below 8 in order to include the 8, so we'll be working with 7.5. 7.5. Approximate the probability that more than 8 will be taking calculus. So this one here, the probability that x is larger than 8, well, again, graphically, here's 8. We want to be larger than it, then we're going to be going in the direction of the arrow here. But I do not want to include 8, so I'm going to have to start above 8 at 8.5. Sorry, I'm going to write 9 down. 8.5. So that's what we'd be starting off with. And then the last one here. The probability that fewer than 8 will take calculus. The probability that x is less than 8. Well, again, if you draw your diagram, you want to be below 8. You don't want to include the 8. So if we're going to be going to the left, we can't include 8, so we're going to have to start below 8 at 7.5. Now the other information you're going to need is the mean and the standard deviation, right? Because you're going to be going to the table. Well, mu is equal to n times p. Show yourself that mu is equal to 13.75. Sigma is the square root of npq. You can show yourself sigma is equal to 2.487. And working with these two numbers and the adjustments we made, you get to the normal table. All right, this particular problem, I'm going to just explain it to you, so pay attention. In Chapter 3, there was a concept called an outlier. An outlier is a data value you feel is extreme in relationship to all the other data values that are collected. So you call it an outlier. Now, one test to determine if a number should be considered an outlier is the interquartile range test, the IQR, and that's what I'm going to perform here. Your first step will be to take Q3 and subtract from it Q1. What is Q1? What is Q2? What is Q3? Well, you asked, so I'm going to tell you. Those are the quartiles. Q1, 25% of the data is below it. Q2, 50% of the data is below it. Q3, 75% of the data is below that number. Well, don't really matter. Step 1, quartile 3 minus quartile 1. 310 minus 250 is 60. Step 2, you multiply this number here by 1.5. It's always 1.5. So whatever this difference is here in 1, you multiply it by 1.5, and you are going to get 90. The third step is you come up with an interval. That interval, you're going to be subtracting the 90 from the 250. So you're going to get 160. You're going to be adding the 90 to the 310, and you're going to be getting 400. So you subtract it from the 250. You add it to the upper number because you're making the interval wider. Then what you do is you look for this number that you are concerned with, that you might think should be treated as an outlier. Is that number in the interval? And the answer is no. It is not in the interval. Not in the interval. So we consider it is an outlier. So once again, you'll be given the quartiles, Q1, Q2, and Q3. You take the difference between these two. Step 1. Step 2, that difference is multiplied by 1.5. Then that number is subtracted from the lower quartile and added to the third quartile. Okay? Then you check to see if your number's in the interval or not. If it is, it's okay. If it's not, you consider it an outlier. All right, another extra problem here. You need to stop the video, think about the problem, and then start working the problem out. All right, here I go. This is quite obvious, an hypothesis test. But much of the work we need to do has been taken care of. 1, we have the hypotheses. 2, we have the test value. Where we're really starting off with is step 3, and that is, what is the rejection region, right? That's really where we're starting off with this problem. Well, that rejection region depends on two things: the alternative hypothesis and the level of significance. So our rejection region is going to look sort of like this. Since it's not equal, we're going to have two rejection regions. If we get too far away, either in the left or right direction, we will be rejecting. Now, what are the actual critical values that we're going to be putting in these boxes here? Well, 1, it depends upon alpha, and alpha is 0.01, but we have two regions of rejection, so we're going to divide alpha by 2, and we get 0.005. Second, we have to decide if we're going to be using a z-score or a t-score. Well, if you look here, we have a sample and a sample standard deviation. We'll work with a sample standard deviation, so we will be looking up a t-score. So we need the degrees of freedom, by the way, which is 17 minus 1, 16. Using this information and this number for our row, we look up our t-score, and our t-score, you do it, is 2.921. Over here, it's negative 2.921. We look for our test value. Negative 157 is somewhere up in here. That's where our test value is, right? Our test value is somewhere up in here. So we are not going to be rejection. We do not reject, right? And if we did not reject, it's a possible type 2 error, correct? All right, so we're given mostly everything for the test here, other than the actual rejection region. Here we go again. We have a test. We're giving you some information regarding this test. I don't know what the test is about, but we have information. And they want to know if we're going to be rejecting the null hypothesis at a level of 0.01. Well, again, we have step 1. What is the hypothesis? We have step 2, the test value. This number here only applies if you're doing the p-test. Now we have some additional information here, but we're actually starting at step 3. That is, the rejection region is going to look like this. It's going to be when we're too far to the left, significantly too far to the left, because again, the alternative hypothesis is saying we should be less than. So we're going to have a left tail or left tail rejection region. The question is, what is this number that goes here, the critical value? It depends on alpha, which is 0.01. It also depends on if we know sigma or not, which we do. So we know this is going to be a z-score. Now it is on the left-hand side. So we look up the z-score associated 0.01. That z-score is a negative 2.362. I'll look for my z-score, my test value. It is located somewhere right here. So we will not be rejecting. So we do not reject. And so another possible type 2 error.